Okay, so let's try another example. So here is my linear equation, right? Here's my variable, right? And right, we know it's linear because the highest power is 1 or exponent is 1. And notice that this problem looks very similar to example 1. The only difference is I added that 2 in there, okay, which changes things. In this specific problem, is actually example 1 in your book, the exact same example. So I'm not going to be using all the same examples, but this specific one I did want to do because I chose x plus 3 purposely equals 17 in the last example to connect it with this one. Okay, so the directions are solve, right, the equation and check. Okay, and again, you use the word solve in mathematics when you have an equation, when you're actually solving for a variable. When we were working with algebraic expressions and evaluating and simplifying, okay, it didn't say solve, it said simplify or evaluate, okay? The directions are important in math, so that's why I have you write the directions, because I can give you an equation and tell you 10 different things to do with it. You just have to, well, read the directions. Okay, so I want to solve for x. Okay, so we have 2 times x plus 3 equals 17. So the first thing you want to do is, again, the goal is to isolate x. So what's next to, well, we have 2x, but what's next to 2x? This plus 3x. Well, I don't want it to be there, so I can add negative 3 to both sides, addition property of equality, which just means I'm subtracting 3 from both sides. And again, I'm working vertically. Okay, so this is great because my 2x, right, is still there. I haven't done anything to it. 3 minus 3 is 0, right? I mean, if you want to write in the 0, you can. You don't have to. I mean, if I add 0, if I give you $0, I'm not really giving you anything, so nothing's changing. Equals 14. Okay, so again, notice, right, our last problem, this was a 1, and our solution, right, was 14. But this is not 14, right? This is 2x equals 14. So this is asking you, well, 2 times, and again, oh, we'll just keep it white. I was going to do purple, but 2 times what number is 14? Well, 2 times 7 is 14. So if you know, I mean, from here, if you know, okay, x is 2 times what is 14, x is 7, that's fine. That's completely fine. That's great because you're actually understanding what this equation means, right? So you can be kind of thinking, right, sort of thinking cloud. If you don't want to do that, okay, I have 2x equals 14. Well, I mean, think about how you got 7, Well, you just really divided 14, right, by 2, right? You cut it in half. So this is where the multiplication property of equality is. You're dividing by 2 again, but you're really multiplying by half. So if I write this out, let's see, in blue. Okay, so we're used to doing, okay, let me divide by 2 to both sides. Why am I dividing by 2? Okay, you're dividing by 2 because this is 2 times, right? There's a little dot here, times x. So times. So you do the opposite operation. Well, the opposite operation of multiplication is division. And we do that because we want a 1 there, right? 2 divided by 2 is just another way of saying 1. So 1 times x is 7, or, right, 1 times x, x is equal to 7. Okay, or this is again really saying, this really means I can also write a half of 2x and then a half of 14, right? Notice again, 2 divided, whoops, 2 divided by 2, well, I still have a 2 divided by 2 here, right? These are just reciprocals, right? If you multiply those fractions, you're just going to get 2 over 2, which is 1, which is the same one that I have right here, this big one. Okay, so I want you to understand that when you divide by 2, right, you're really just multiplying by a half, okay, because you're cutting it in half. Okay, so this was a two-step equation because I did two steps, right? Notice my blue parts, I did -3 and then I divided by 2. Okay, now let's check our solution. So let's check x equals 7. Okay, so this is our proposed solution, or this is what we claim. I'm claiming that x is equal to 7. Okay, well, let me check it, right? Or I want you to prove it to me that it does in fact work. Well, this again goes back to evaluating an algebraic expression. So I have 2x plus 3 equals 17. 2x plus 3 equals 17. Okay, so x is, so I'm checking this guy. So that means I'm going to substitute it back into the algebraic expression, which is on the left-hand side. 2 times 7, right? Always use parentheses, plus 3, right? Does that really give me 17? Okay, when you check your solutions, when you check, you're literally evaluating, okay? You're substituting, or some students say plug and chug. You're not subtracting 3 from both sides. You're not using any of the properties of equality because you're checking. So you don't want to move things around. So, well, obviously this is 14 plus 3, right? 7. And, well, 14 plus 3 does give you 17. And notice here again, I used the, let's go ahead and maybe note that, order of so operations. And because the order of operations says I have to multiply, right, before I add. So make sure not to do 7 plus 3 to get 10 and then multiply by 2. Because if you do, you'll get 20, and then 20 is not equal to 17. So we generate a true statement. Okay, therefore, whoops, therefore, or thus, or hence, therefore 7 satisfies, right? It's a math term. Satisfies the equation 2x plus 3 equals 17, okay? Again, meaning if I substitute 7 into that equation, I'm going to generate a true statement. Or even, we can also say the solution set is, well, there's only one solution, so 7. So this is a singleton, right? When we connect it back to set theory. Okay, that is example 2, or really example 1 in your book. So I'll do a next one, and again, I'm just going to be doing these from easy to hard.